With this video, we will briefly review a calculation of a trench for a 12-meter high excavation underwater. Paratie Plus can allow the presence of opposite wall that can be either the wall that encompass an excavation, or in other cases a wall that include an embankment. In this case, we will consider the case in which an excavation is made inside the clearance between the two walls. So the two walls are at a spacing of 15 meters, and we will have to excavate down to -12. You see that there is a water table, so the excavation will be done underwater. Here in dashed line you will see an anticipation of what are the elements that need to be defined in the model, namely the walls and some strutting positions. We will foresee to provide two levels of strutting systems. Now, first of all, we assume that a water table rests at a depth of 5 meters down to the grade. We also assume that there is a superficial layer that is represented by sand, and down to -9 there is some gravelly sand. Those properties of these soils can be defined as a normal procedure by Paratie Plus. Just to review the data we have included, we have considered the sand with the typical value for sand, loose sand with friction angle of 30 degrees, and elastic properties in terms of Young modulus at virgin loading, that is 15 megapascal, and the unloading reloading modulus that is 45 megapascal. That means 3 times the 15 the virgin compression modulus. And we can also specify some other parameters like the K0 coefficient and permeability coefficients. As for gravelly sand, we have more or less the same permeability, but we have a much higher resistance in terms of friction angle, and also much higher stiffness in terms of Young modulus. So this is the stratigraphy. Now the second task to perform is to include the wall inside the excavation. So in this case, first of all, we defined two walls. One wall is at x coordinate -7.5, and the second wall, that is the right wall, is at +7.5. It means that the distance between the two walls is 15 meters. Now we define the retaining walls at each part. In this case, we will, due to the symmetry, we will consider the same shape for all the parts, but we can also provide different shapes for the retaining wall on the opposite walls. Let's see what we did in this case. In this case, we consider the sheet pile down to elevation minus 18. What is the shape of the sheet pile? In this case, we consider an AZ sheet piles taken from a catalog, and the material that is S275 megapascal resistance, that is an intermediate capacity steel according to European code. So you can pick this number from a catalog, and automatically Paratie Plus calculate the inertia and so on. By the way, we can see that here in this dialog box there are two parameters, namely beta B and beta D, that are some reduction factors due to the peering capacity and to the deflection capacity of this shape in case of U-shaped. In this case, there is no need to define these values because such values are by default taken as 1. We will see the meaning of this parameter in another video. So this is simply what we do. Of course, this, as usual, we make an initial assumption regarding the effectiveness of this wall, and we will do the calculation and see what happens. If the wall is not sufficient, we will modify the wall and so on. So now, as usual, we define first of all an excavation down to elevation minus 2 in order to allow the installation of the struts. And at elevation the stage number 3, we apply a strut, the first strut. So let's see what is a strut. The strut is simply a truss connecting opposite walls and as a section. So what is important to understand is that the axial capacity and stiffness of the struts depends on the out-of-plane spacing that must be given by the user. In this case, we will assume a spacing that we will put as actual strut at 5 meters distance spacing in the out-of-plane direction. And as for the section of the wall, we will consider a circular hollow section, 273 millimeters diameter times 10 millimeter thickness tube, and this is the section. Of course, when we define the spacing at the strut, we must here put 1 as the spacing for the cross section. So what in this case what we did is simply say that at 5 meters there is a pipe with this diameter and this thickness, and with this property and this material, of course, steel. In addition to the axial capacity of the strut, we can consider the effect of the so-called whalers. In other words, such flexural element that is capable to distribute the load of point load of the struts along all the wall. We can connect a whaler to each wall. In this case, for example, we have considered a wall section steel, which is actually, we assume that the out-of-plane scheme is continuous. Let's say that we can consider a continuity between the supports that are assumed to exist at each position of the struts, and we apply the cross section of the struts. We may have some choices. In this case, we consider a single H section, HE500A, one section profile. We can also very big, of course. We have some position. We have some how to say, some options and so on. In this case, we consider one wall, one beam. And the same can be done for the other section. So Paratie Plus make a display drawing of a plot of this the assumed profile. And after that we can proceed and go on and consider an additional excavation. So now to install the next prop, we must excavate down to elevation minus 7.5. So it means that we have to lower the water table inside. In this model, it is simply accomplished by simply dragging down the water table at this elevation. This means that there is some pumping system that make possible the assumption of having a continuous water table at this elevation. I want to stress that this is not a true seepage analysis, but is simply a method to calculate the pore pressure according to a simplified scheme of seepage that is depends just on the path of the flow very near to the wall. This is normally a typical assumption that is also considered to be quite conservative. In another video we have seen that there are also other possibilities. Again, we can add an additional strut, and in this case, for example, we consider the same shape as before. So, and then we excavate down to elevation minus 10, and then excavation minus 12. So this is a temporary excavation, so we don't take care of long-term structure inside at the moment. So doing this, we can already do an analysis and by simply clicking the model. Okay, and we can inspect what happens at each stage. For example, we can look at displacement. Of course, at stage 0 there are no displacement because at the beginning there is a perfect balance at each side of the wall, so that there is nothing that can induce displacements of the wall. Then it's at stage 2. We see some cantilever deflection, 2 millimeters at the top, that are of course symmetrical. In this configuration, we can also see how is the distribution of horizontal effective stress. Of course, there is some parts that undergo active condition and very limited parts that takes passive conditions. And again, we can also see the water table. Of course, the water table has not changed because at the moment no modification to the water table, so it is simply an hydrostatic condition. At stage number 3, we simply add a strut, but nothing is changed in the model, so the the results in this stage are the same as before, because nothing else has been changed in the model. So it is simply just a stage that actually can be grouped to another stage, but in this case I consider just to see if the prop is activated correctly. Now let's see what happened in excavation. We will see that actually the deflection of the displacement of the wall is dramatically changed, and we have a deflection typical of a propped wall in which there is some support at this level and a bulging deflection in this part. We have a 14 millimeters displacement in this wall, in this part. Of course, there is also the bending moment distribution, and we can check also the axial forces. This is the results at this stage. It is negative, means compression, and we have around 100 kilonewtons per meters. If you remember that we considered one strut at 5 meters, it means that each strut, actual strut, may undergo around 500 kilonewtons of compression. And next step, we add the second strut, but you see that in the second strut, if nothing else has been changed, actually there is no load in the strut, because the strut is, when it is activated, is assumed to have no stress at all inside it. While at next excavation, the strut changed very much its force. It takes 75 kilonewtons per meters, whereas the other one takes more or less the same value. And finally, if we proceed further with the excavation, we have this big load. It's more or less doubled with respect to the previous value. So now we can also, for example, see what happened to displacement at this last stage. We have so it is of course very exaggerated, but we have a displacement of inside toward excavation of 29 millimeters, 3 centimeters toward excavation. We can see the effective pressures and the pore pressure. The pore pressure are affected by a seepage going into the soil. In this case, we may have also some hydraulic gradient. In this case, the hydraulic gradient is calculated automatically by Paratie, assuming this pattern, and the value is constant and is 0.4. That is a typical value that can be accepted. So now the next is to look at the moments, and when we have these maximum values, we can check if it is acceptable with respect to the capacity of the sheet pile we have assumed. But this can be done automatically if we select properly the design code to check with respect to the selected value. So we can, in this case, we have assumed that we will work according to Eurocode, and in this case we will check with respect, we will design this wall with respect to design approach number 1, in which two cases are to be solved. It is combination 1, that means we have to increase the load and keep the resistance factors, stability factors as unit. And the second case in which essentially the load are kept constant, but the soil parameters are affected by a safety factor. Paratie Plus calculates both these scenarios and give us the results for all of them. In addition to the definition of the design section, the design's assumptions, we have to select which kind of design code has to be considered for each member. This can be done by simply going to design and select design property. So we have the possibility to select Eurocode number 2 for concrete and Eurocode number 3 for steel code, and in this case Eurocode number 7 for ground anchors. In this case we have no ground anchor, so this is less important. So once we have defined this, there is not only the default load cases, load configuration, but there are also some other analysis that will be performed. One is for equilibrium, one is design assumption 1, combination 1, and one is design assumption 1, combination 2. This analysis corresponds with different Paratie run. So we can now run everything, both, in this case we run both analysis and verification. The program to run takes a little bit more time to run because not only the analysis, Paratie analysis is done, but also a verification check has been done. So now we can have a simple depiction of the capacity of the wall by checking the resistance. In this case, it is applicable just to resistance combination like A1, M1, R1. And we will check what is the... First of all, we have to check what happens to the capacity with respect to the wall number of selected stage and assumption. So what we see is that maximum resistance factor is 0.78. It means that we have reached about the 68% of the capacity of the resistance of the wall. So it means that the wall is safe in this case. This, of course, can be done stage by stage, or simply as a wall for all an envelope of data. Second, now we want to see if the props, the struts are sufficiently safe. So in this case, the representation is a table in which we can check all the structural elements. What we see is that for combination of A1M1, that is it is normally the combination that governs for structural capacity. We see we have the ratio of the capacity on the actual the ratio of the existing load with respect to capacity. We see that in this case, for example, one strat is the ratio is 1. It means that the capacity is little bit not sufficient. And also we can have a depiction of the capacity of the whalers, So for each whaler, the program makes a summary, including the material, the spacing, and the load. That is actually the load is simply the load on the struts, and the moment and shear capacity for each wall. We see that more or less we have captured selection of the shape, because we have exceeded a little bit the capacity by 14%. So in this case we may have to change this shape to a bigger value. So this, for example, can be done simply by clicking this and modify the wall, and rather than using, we can select the B version. Okay. We see that automatically this, if we have assigned the same whaler section for each edge, it is automatically changed also on the other side of the prop. Okay, we can run the analysis again and see if everything is okay. We see, let's take a look to the whalers, and we see that actually the capacity, the bending capacity ratio is now has gone down to 0.9. So in this case our design is okay. Of course, one has to make more calculation, more checks, but just for a glance we can see that more or less are on the correct way. Thank you for watching.